Hello again, this is Professor Roman. Let us resume the lecture series, Transition to Advanced Mathematics. It's time now we considered proof by contraposition. The first example of a theorem whose proof is by contraposition is going to be very useful in other results, so I'm going to call it a lemma. It's a simple result that's very useful, so the term lemma is appropriate. Let m be an integer, then m squared is even if and only if m is even. M squared is odd if and only if m is odd. We're going to do a two-part proof here of the biconditional. Let's take the first one. If m is even, then m is 2k for some integer k, and so m squared is 4k squared, which is even. Simple. To prove the converse, which is m squared even implies m even, that's a little trickier. To write m squared equals 2k is not going to help, because if we take the square root, we're not going to get anything meaningful for us. To prove this, it turns out to be easier to prove the contrapositive, which is m odd implies m squared is odd. So if m is odd, m has the form 2k plus 1 for some integer k, and so m squared is quantity 2k plus 1 squared, which is this number, which is clearly odd because the first two terms are even. The third one is odd. The second statement follows actually from the first, and I'm going to let you think on that. Let me point out one thing here that I've discussed before. Remember I said never introduce a symbol unless you explain where it comes from or what it represents. And that's this phrase here. I will see on many students' papers, if m is odd, then m equals 2k plus 1, and so. And if I was going to be a stickler, I'd say, well, what's k? So that's why I said for some integer k. Right? Another theorem, if n is an integer and n squared minus 6n plus 5 is even, then n is odd. Okay, this starts with a declaration of what method we're going to use. We prove the contrapositive, which is m even implies n squared minus 6n plus 5 is odd. Since n is even, our lemma tells us that n squared is also even, and since 6n is certainly even, n squared minus 6n is even, and so n squared minus 6n plus 5 is odd. Notice something else here. I went very in great detail to show that if n squared is even, this whole thing is odd. Even minus even plus odd is odd. You might ask yourself when you're writing these proofs, do I need to tell the reader that an even number plus an even number is even, and odd plus odd is even plus odd is odd? You know, that's a value judgment. At some point you have to assume the reader knows something, and those are simple facts, and frankly, if the reader doesn't know those facts, they should be able to prove them themselves. I didn't agonize over this one. I just simply said 4k squared plus 4k plus 1 is odd. Down here, I went into more detail, and I did it deliberately so I could have this discussion we're having now. I probably should have done this up here and not down here, but it doesn't matter. The point is, you are always going to have to judge when you write a proof just exactly how much detail do you need to include. And there are two aspects to that. One is, if you are a student writing proofs that are going to be graded, you know that the person who's grading doesn't need all this minute detail. They will understand what you're writing. On the other hand, you need to convince them that you know what you are doing. So a little extra detail is not such a bad thing. It's very unlikely you'll be penalized for too much detail in your proofs. You might get a comment in the margin, you don't need to say all this, but I doubt very much you'd lose points for doing it. From a student point of view, you might include more detail than you would normally. From the writer's point of view, from the instructor's point of view, we talked a little bit about the issue of detail and filling in gaps or leaving some gaps open for the student, for the reader to struggle with. So we've been through that conversation already. Okay. But I do get asked frequently by students, how much do I need to say? And they're not always happy when I say, well, it sort of depends. You're going to have to use your judgment on that. Include enough detail so that it's clear to me when I read your proof that you know exactly what you are doing. Okay? But you don't need to include any additional detail beyond that. And that's a value judgment. Okay. Next theorem. If a is an odd integer, then x squared plus x minus a squared equals 0 has no integer solutions. So we will prove the contrapositive, and this isn't the only way to prove this theorem. As I mentioned once before, sometimes multiple templates will work, but we're practicing proof by contraposition. So start out, tell the reader what you're doing. We prove the contrapositive. That is, if t is an integer solution to this equation, that is, if t squared plus t minus a squared equals 0, then a must be even. So you look at this and you say to yourself, how do I prove that a is even? One thing I remember is our lemma that a is even if and only if a squared is even. So it's equivalent to prove that a squared is even. And so I can move the a squared to the other side, and all I have to do is show that this is even. Well, this factors, and now, regardless of whether t is even or odd, one of these two factors is even, because they differ by 1, and therefore the product is even. So a squared is even, and again, the lemma then tells us that a is even, and we're done. For the next theorem, we need a tiny bit of notation, very common notation. For integers x and y, the notation x vertical bar y means that x divides y. Or put another way, y is an integer multiple of x. And if I put a slash line through the vertical bar, it means x does not divide y. So here is the theorem. If a, b, and n are integers, then n does not divide the product ab, implies n does not divide a, and n does not divide b. If n does not divide a product, it can't divide either factor. That sounds pretty obvious, but again, we don't rely on obvious. Okay? Obvious is a term that we professors use to torture our students, okay? But otherwise we don't use it. Actually, we use it to torture other mathematicians as well. But, okay, so we prove the contrapositive, namely A divides N or N divides A or N divides B implies N divides the product AB. Now, as a thinking out loud remark, I didn't explain that the contrapositive, which is directly, it would just be not this implies not this. I used De Morgan's law here. Not this is a negation, this is a negation, this is a conjunction. When I take the negation, it turns into this by De Morgan's laws. I didn't explain that in detail, and it's not necessary. At this point in the book, if I take my point of view, the instructor, you should already be familiar with De Morgan's laws. Mathematics builds on itself. That should be in your toolbox, De Morgan's laws. I don't need to go into infinite detail here whenever De Morgan's law applies. Something for you to sort out. Okay. Anyway, so if n divides a, then a is a multiple of n, kn, for some integer k. Again, I'm explaining what k is. And so AB is knb, which shows that n divides AB. Similarly, if n divides b, then b is k times n for some integer k, and so AB is akn, which again shows that n divides AB. Okay? Simple enough. Alternatively, we could have saved a little bit of time and effort, not much, but a little bit. So let's look at this alternative proof. Again, we prove the contrapositive, and here it is. Since the value of AB does not change if we interchange A and B, that is to say, since AB is symmetric in A and B, we may assume without loss of generality that n divides A. Because if n doesn't divide A, then it's got to divide B, and we can interchange the roles of A and B. So we've talked about this symmetry business before. So then the rest is the same. But that, if you can compare, it's a tiny bit shorter. But in other instances, it may be a great deal shorter. So this symmetry argument, when it's available, can be quite a time saver. Another result, if n is a positive integer with the property that the remainder, upon division by 4, is either 2 or 3, then n is not a perfect square. That is, n is not the square of another integer. Again, we prove the contrapositive, namely, if n equals m squared is a perfect square, then its remainder upon division by 4 is either 0 or 1. That would be the negation of the remainder being 2 or 3. So, to this end, in other words, to the end of proving the contrapositive, the division algorithm gives us this. So here again, we're using a tool from our toolbox, and the remainder lies between 0 and 3. Now, if m is even, remember what we're trying to show, the remainder upon division by 4 is either 0 or 1. It would not be reasonable to repeat that after one more sentence. So I'm just reminding you. So if m is even, m is 2k for some integer k, and so this equation becomes this. Okay? And that can be written like this, and therefore r is a multiple of 4. But since r lies between 0 and 3, the only way it can be a multiple of 4 is if r is 0. On the other hand, if m is odd, and I could have set this up a little differently. I could have, at this point, I could have said, we consider two cases. Case 1, m is even. Case 2, m is odd. Actually, that might not have been a bad idea as you learn to construct proofs. This is simple enough so that, each case is a sentence or two. You probably don't need to set them out with headings called case 1 and case 2. But frankly, if I was rewriting this, I probably would do it, just because of the level of the textbook. Once you get to upper division math, you're not going to see that done very often unless the two cases are more lengthy and significantly different. On the other hand, if m is odd, then m equals 2k plus 1 for some integer k. And so, again, this equation, 433, looks like this, or equivalently multiply out, which can be written, move it around. And you might think of solving this for r, but that's not going to get you directly what you want. So I left it r minus 1 on this side and factored out the 4 here. So now we see that 4 divides r minus 1. And that implies that r minus 1 has to be 0 for the same reason we saw earlier. R lies between 0 and 3, so r minus 1 lies between negative 1 and 2. But if it's divisible by 4, the only way that can happen is if it's 0, or in other words, if r is 1. So I say thus r equals 0, r equals 1. This proves the contrapositive, and so the theorem is proved. Okay, let's consider now some examples of proof by contradiction. As you know, to prove a statement by contradiction, we assume it is false, and we try to deduce something that is obviously false, like 0 equals 1, something that is indeed a contradiction. And then we will know that our assumption was at fault. Our assumption was that the theorem is not true, and therefore the theorem is true. Here's the first example. There is no smallest positive rational number. So we will start, you could start these proofs with the phrase, we will prove this theorem by contradiction. That would be perfectly fine. Or even the 3 words proof by contradiction, period. But I like to say something like, suppose to the contrary, that there is a smallest positive rational number, and call it r. Now we need a contradiction. It's not really too big a leap to see that if there is a smallest positive rational number r, then what about r over 2? It's positive, it's rational, but it's smaller than r, and that's where the contradiction will come from. So in detail, since r is a positive rational number, it can be written in the form r equals a over b, where a and b are positive integers. Therefore, r over 2 equals a over 2b is also a positive rational number, but r over 2 is less than r, which contradicts the definition of R. It's important in proofs by contradiction to state what is being contradicted. Oftentimes you'll just see comma, a contradiction. And it's better as you're learning to do these proofs to say specifically what's being contradicted. So which contradicts the definition of R. R is defined as the smallest positive rational number. So the existence of R over 2 contradicts the existence of R. And finally, hence, there is no smallest positive rational number. Okay, next example. In a right triangle with sides of positive length, A and B, the hypotenuse and hypotenuse of length C, we have C is less than A plus B. Suppose to the contrary, that C is greater than or equal to A plus B. Again, we need a contradiction, but this time it might not be quite as easily seen as it was in the previous case. What are we going to contradict? It's not clear, so we need a little bit of, how are we going to contradict, I should say, this statement that C is greater than or equal to A plus B? Well, a little bit of playing around, checking some ideas. Since A and B are positive, one thing we could do is square both sides of this. Why? Well, it's an idea. Turns out that it works. It may not have been your first idea, but that's what proof making is all about, finding the right idea. And oftentimes it won't be the first idea you try, nor the second or third. It may take several attempts. Sometimes you have to live with it for an hour a day. Sometimes if you sleep on it, you wake up in the morning and have another idea. Anyway, squaring both sides, since A and B are positive, A plus B is positive, everything's positive. So when we square an inequality, the sense of the inequality remains, and we get C squared bigger than or equal to quantity A plus B squared, multiply it out. Now, at this point, we might notice something, and that is just looking at C squared bigger than or equal to A squared plus B squared plus 2AB. And there's a couple ways you could do this. You see the C squared and the A squared plus B squared, and now you should be thinking Pythagorean theorem. C squared is equal to A squared plus B squared. So how can it be bigger than or equal to A squared plus B squared plus 2AB? 2AB is positive. It's non-zero and it's positive. So somehow we have to find some wording that says we're contradicting the Pythagorean theorem. So one way is simply to note that this is strictly greater than this, and so C squared strictly greater than A squared plus B squared contradicts the Pythagorean theorem. You could stop there, but I added which states that C squared equals A squared plus B squared. And so we must have C less than A plus B as desired. You can change the wording. It's, if I rewrote this, I'd probably change the wording. Every time I write it, I use slightly different wording. But anyway, hopefully you get the essence here of the proof. Here's another one. If A and B are integers with A bigger than or equal to 2, then A cannot divide both B and B plus 1. And these are the symbols. A does not divide B, or A does not divide B plus 1. This theorem could be reworded if that any integer A greater than or equal to 2 cannot divide two consecutive integers, b and b plus 1. So again, suppose to the contrary that this is false, and I've identified it by number. 4.37 is false. That is, that a divides b and a divides b plus 1. This is De Morgan's law in action. The negation of this is this. Remember, or switches to and. We must find a contradiction. Now this is thinking out loud. We could simply say that since a divides both b and b plus 1, it must divide their difference, which is 1. And that's not possible. Since a is bigger than or equal to 2, it cannot divide 1. And that would be a perfectly acceptable proof. But if you're writing a proof on a test, if someone else is going to judge your proof writing skills, you might want to elaborate just a little bit. And here it is. Since a divides b, we know there's an integer I for which b equals ia. That's the definition of divisibility. And since a divides b plus 1, there's an integer j for which b plus 1 equals ja. Therefore, ja is b plus 1, and we substitute, and we get ia plus 1, or equivalently, we do some algebra. Now you can see that a divides 1, which is false. Or what I wrote here is, but both factors, j minus I and I, are integers, and so in particular a must be plus or minus 1, because it divides 1, which contradicts the assumption that a is bigger than or equal to 2. Okay. You might think this is agonizing detail, and maybe in this case it is. But as the proofs get more difficult, that detail is going to pay rewards both in your own clarity and understanding what you are doing, and in other people who have to judge you and are reading your proofs. Okay. Here are two very famous theorems whose proofs are generally done by contradiction. The square root of 2 is an irrational number. Assume to the contrary that the square root of 2 is rational. Then there are integers a and b with b not 0, for which square root of 2 equals a over b. And we may assume that a and b are relatively prime. Assumptions like this are often made in proofs. This is, again, thinking out loud. But if an assumption seems at all subtle, some explanation should be given. In this case, I'm on the fence. What I could have written here was assume that the fraction a over b is in lowest terms, and so a and b are relatively prime. But I think most students that you will understand fractions reduced to lowest terms. I don't think that needs to be elaborated on, but some people would probably differ. And again, it depends on your audience. So leave that up to your discretion whether to elaborate on this assumption. But if the assumption is deeper, if it's more subtle, then you really should say something. Okay. Of course, if you're writing a research paper, if you have your PhD in mathematics already, and you're writing a research paper, you would probably very seldom, if ever, explain an assumption. In any case, multiplying both sides of 4.39 by b, you're looking at this trying to find a contradiction. And there's not much you can do with this. One idea is to multiply by b and get something that looks like this. What does one do now? Well, I guess one says, gee, I hate that square root of 2. I wish there were no square roots because it'd be easier to work with. So what do? You square both sides. And you get to here. And then you notice, well, let's see, this tells me that a squared is even. And I remember a famous lemma that a squared is even if and only if a is even. Okay, so a is twice some other integer. We're not sure where this is leading at this point. But we are doing something, and doing something is a whole lot better than doing nothing. So we're just exploring, which is what proof making is about. Exploring ideas, staring at something until you think of something to do. Oftentimes it will lead you down the wrong path, but oftentimes it won't. So anyway, I've squared this, and I've noticed that a squared is even, therefore a is even, so a is 2m. Why not stick that back in here? And I get 4m squared equals 2b squared. May as well cancel the 2, and now, aha, this is where the light should go on. Well, then b squared is even, and so b is even. But how can both a and b be even if they're relatively prime? They don't have any common factors. So, thus both a and b are even, which contradicts the fact that a and b are relatively prime. Hence, square root of 2 is irrational, or not rational. This is one of the best examples of proof by contradiction. You might want to spend a little time trying to find a direct proof of this and see how well you do. Here's another terrific example where proof by contradiction really shines. There are infinitely many prime numbers. This was first proven by Euclid in 300 BCE. So what is that? 2,300 plus years ago. Suppose to the contrary, that there are only finitely many prime numbers, and we can write them down, p1, p2, up to pn. What to do? Well, one idea would be to somehow produce another prime number that wasn't on the list. Not clear how to do that. Maybe we probably need something kind of large, bigger than these. So here's an idea. Multiply all these primes together and add 1. Again, we don't know where this is headed just yet. But what about this integer d? Well, every integer is either a prime or divisible by a prime. This can't be a prime because it's bigger than all of these, and these are the only primes in the world. So this has to be divisible by a prime. It has to be divisible by one of these. But this product is divisible by one of these. So if d was divisible by p sub k, then the product here, p1 through pn, is divisible by p sub k, which means their difference is divisible by p sub k. In other words, 1 is divisible by the prime p sub k, and that's nonsense. So that's what I wrote here. Maybe a little bit better than I just explained. The integer d is either one of the primes listed above, or else it is divisible by one of these primes. But since d is larger than any of the primes in 442, it must be divisible by one of these primes, p sub k, where k is somewhere between 1 and n. Thus, pk divides both d and the product, p1 through pn. which implies that pk divides their difference, that is pk divides 1. Since this is not possible, we have a contradiction, and so there must be infinitely many prime numbers. I said before, I'd like to say again, as you go through these proofs, look at not only the mathematics, but the writing style, which again I will say is not the only style. It may not be the best style, but it's a guide that will help you develop your own style. Complete sentences, complete explanations, details. Okay, let's now take a look at proving biconditional statements. As you may remember, there are generally two ways that can be done. The most common way is to break a biconditional into a conditional and its converse, but sometimes you can just barrel through the biconditional and arrive at a proof that way, just by a series of equivalent biconditionals. If x is a real number, then x squared minus 6x plus 9 equals 0 if and only if x equals 3. This is a chain type proof. X squared minus 6x plus 9 equals 0 if and only if, x squared minus 6x plus 9 equals 0 if and only if the quantity x minus 3 squared is 0. In other words, I just factored this. And that holds if and only if x minus 3 equals 0, and that holds if and only if x equals 3. And here's the square, by the way, that ends the proof. It's over here, justified. I don't like putting the square right here because it interferes with the beauty of the equations, but it's up to you. In any case, this could have been done in two parts. One could have said if x equals 3, then plugging in shows that x squared minus 6x plus 9 equals 0. Conversely, if, say, r squared minus 6r plus 9 equals 0, then r minus 3 squared is equal to 0, and therefore r minus 3 is 0, therefore r is 3. So it's not much longer, but this is a little bit cleaner, a little bit neater. So, next theorem. Suppose that A, B, C, and I should have said really and D, that would have been nicer, are real numbers with A not 0 and C not 0. Then the lines y equals ax plus b and y equals cx plus d have the same x-intercept if and only if AD equals BC. So let's look at the proof. The x-intercept, x naught, of a line y equals alpha x plus beta, where alpha is not 0, is found by setting y equal to 0. That is, by solving this equation to get x naught equals negative beta over alpha. This is a little lesson in how you find the x-intercept. If you think your readers already know, I suppose you could just jump right to here and say the x-intercept x naught of a line y equals alpha x plus beta is equal to this, and let the reader sort out what he or she might be missing. So that's another value judgment. But this would be very nice if I was a student writing a proof on a test. I would include this. Therefore, the lines y equals ax plus b and y equals cx plus d have the same x-intercept if and only if negative b over a equals negative d over c, and, which holds if and only if bc equals ad, cross product, which is what we wanted to prove. Now, this is a chain type proof again. It's a sequence of if and only ifs that are logically equivalent. Doesn't quite look the same as the previous one where I was able to display all the biconditionals in a display here. But you see if and only if and only if. So they are biconditionals. Here's a two-part proof involving a biconditional. Two integers, m and n, have the same parity. That means they're either both even or both odd. The parity is the evenness and oddness. If and only if m squared plus n squared is even. So we'll do this in two parts, and you don't need to say that generally. It's not a bad idea, but it generally becomes obvious pretty quickly. First, assume that even in the chain type proofs, this is a thinking out loud. So this is officially not part of the proof. Okay. So I would not be including these comments in proofs except as a teaching aid. First, assume that m and n have the same parity. If both m and n are even, then we can write m is 2i and n is 2j for some integers I and j. It follows that m squared plus n squared is 4i squared plus 4j squared, which is clearly even. So we've said that if both m and n are even, then m squared plus n squared is even. On the other hand, this is a very nice phrase because it tells the reader a lot. It tells them that we've checked one possibility, now we're checking another one. On the other hand, if both m and n are odd, then we have this. And so, again, m squared plus n squared, work it out. That looks pretty even. So this proves that if m and n have the same parity, then m squared plus n squared is even. So that's that's one direction of the biconditional. Okay. This might be amenable to shortening. I haven't thought about it, and I'll let you think about it. If you can figure out a way to shorten this, that would be good practice, but it's certainly not necessary. It's not that long. Now we say for the converse, and that's critical because it's telling the reader we're going now in the other direction. So we assume that m squared plus n squared is even, so it looks like this. And here is a statement that's also important. We must show that m and n have the same parity. We're saying what it is we need to do. This isn't what I would call a really long proof, but we have gotten a little bit away from the statement of the proof, so it's a good idea to remind the reader what we have to do. How does one show that two integers have the same parity? Well, they either have to both be even or both be odd. So we could consider two cases. Case 1, m is even, then we need to show that n is even. If m is even, then m is 2i for some integer I, and so this equation gives us this little bit of algebra, replaced m squared by 4i squared. Solve for n squared, replaced m squared by 4i squared. And this is, of course, even. Therefore, our old friend the lemma at the top of our toolbox says that n is also even. And so m and n have the same parity in this case. And this is just a nice little, this shows that your writing style is clear, is polished. It ties back to here and reminds the reader we have another case to consider or that at least we've considered only one case. Case 2, m is odd. Leave that for you. Okay. Alternate proof. Note first that the sum of two integers is even if and only if the integers have the same parity. Actually, I think as I read this, I'm sorry I didn't say note first that two integers have the same parity if and only if the sum is even. That sounds a little more like the point of this sentence, but it's okay the way it is. It's fine. But lemma 4.27 implies that m and m squared have the same parity, as do n and n squared. Hence, m and n have the same parity if and only if m squared and n squared have the same parity. Therefore, m and n have the same parity if and only if m squared plus n squared is even. You may need to reread this a couple of times so that it really becomes clear. But once that happens, you can see this is, of course, a much more concise proof. You know, this is half a page. This is 3 lines. So it illustrates there are many ways to write a proof. Some are going to be longer than others. Some are going to be clearer than others. You may find this to be so unclear that you wouldn't write it yourself, but it's perfectly fine.